Okay, there are two broad types of electricity. You know, we have a static electricity. Static electricity. Static electricity involves charges that are transferred and they stay in their position. What are charges, by the way?
Charges are electrons, motion.
Charges.
Motion.
You know, charges are particles. Exactly. Charges are particles with unequal numbers of protons and electrons. You know, once in a particle, the number of protons is not the same as the number of electrons. We say that it is charged. In chemistry, you say it is an ion. You do chemistry? All right. So that's what we also call it in chemistry, ion, ion, or charge. We normally use charges in physics, you know. So an object is charged if it doesn't have the same number of protons as electrons, or if it doesn't have the same number of positive charges as negative charges. In terms of an atom, the protons are positively charged. You know that. The electrons are. What is the charge of a proton?
Positive.
What about electrons? So when you have the same number of protons as electrons, what is neutrally charged? If you have more protons than electrons, it's positively charged. If you have more electrons than protons, it is negatively charged. You can also think about it like this. If it has more positive charges than negative charges, it is positively charged. If it has more negative charges than positive charges, it is negatively charged. If they have the same number of positive charges as negative charges, it is neutrally charged. So static electricity involves charges that are transferred and they stay in their position. They don't flow. That is compared to current electricity, which we'll look at later. So let's look at static electricity. I said they involve charges that are transferred and they stay in their position. So static electricity, I will just write a simple note. Static electricity involves charges that are transferred. Remember, I said charges are particles with an unequal number of protons as electrons. Static electricity involves charges that are transferred and they stay, or that are transferred and stay in their positions. Let me just say, charges that are transferred and stay in their transferred position. Okay, so that's for static electricity. Charges that are transferred and they stay in their transferred position. And of course, I define charges as particles you know, particles with unequal number of particles with unequal number of protons, or you can say number of positive of protons in bracket positive charges and electrons, negative charges. Once they are not equal, it is charged. In physics, a particle can be anything, a matter, an object, water, anything that has mass is a particle. It could be as tiny as an electron or as big as a universe, you know.
You said a charge.
A charge. And no, what I mean is a particle. When we say a particle, it could be an atom, an ion, a molecule, you know. So, when those charges are transferred and they stay in their position, we have static electricity. You will need to understand what that means. This is what I am talking about. Let's look at production of static electricity. That will help you to understand it. Production of static electricity. Let me write it in the next page. We might find something to fill up on this page later. So let's go to the next page. I'm on the next page. Production of static electricity. Before we talk about that, I knew there would be something I will fill up in the previous page. So go to the previous page. I need to add that charges are measured in coulomb. Measured in coulomb. C. After the name of a scientist. Charges are measured in coulomb, or quantities of charges are measured in coulomb, or quantity of charges is measured in coulomb. Let me just write it as the quantity of charge is measured in coulomb. The quantity of charge is measured in coulomb. So the quantity of charge is measured in coulomb. It could be so small that you can talk of micro coulomb, nano coulomb. You know, nano is very raised about -9, isn't it? Just to remind you. So if I have a charge of 20 micro coulomb, for instance, that's say 20 times 10 raised by -6 coulomb. You remember? Micro is raised by -6.
What else is for pico?
No, pico is raised by -12. Nano is raised by -9. So this is if I have 50 nano coulomb, that's 50 times 10 raised by -9 coulomb. Like you talk about pico, if I have 25 pico coulomb, that's 25 times 10 raised by -12 coulomb. So you can also have mega, kilo, giga, tera. All right. Okay. They can be very small or very large, depending on what you're trying to get. So before I move on to the next page, I've said that there are two broad categories of electricity. We start with static electricity. We look at the next one, current electricity. That will be a different discussion. So static electricity involves charges that are transferred and stay in their transferred position. And obviously charges are particles with unequal number of protons, positive electrons, and electrons. Negative charges, okay. Electrons are negative charges. Now, this is what I mean by transferring. So we look at the next page, production of static electricity. One way of producing static electricity is by rubbing or friction. So rubbing or friction. In this method, you know, just like one simple experiment we used to carry out with much sugar. Do you have a pen there? Can I use a pen? Yes. Just your Bible pen. Oh, is this type you have? That's the one you'll be using. No, don't worry. Can you pass me that small paper? The book. All right. Thank you. I hope I can say this from there. Okay. I don't know if you have practiced this. We used to do that when we were much younger. I've done it a number of times with students. If you rub, are you listening to me? you rub the ball pen on your head like this, you can pick up a piece of paper. You've done that before. You rub it on your hair, and then you bring it close to a small piece of paper, you can pick it up. Now, you need a better pen to achieve that. Now, what is happening is this. When you are rubbing this thing against your hair, some charges are transferred. Charges are transferred means some electrons can either move from the pen to your hair or from your hair to your pen. Initially, the pen had the same number of protons as electrons, so the pen was originally neutrally charged. Same with your hair. Your hair had, your strands of hair had the same number of protons as electrons, so they were all neutrally charged. But when you rub this against your hair, some electrons, which are particles, jump from, let's say, from the hair to the pen. It could be from the hair to the pen, depending on which one is more electronegative. From the hair to the pen, or from the pen to the hair. Assuming some electrons jump from the hair to the pen, what will the pen become?
From the head to the pen.
Yes, if some electrons, the pen becomes negatively charged because it gained electrons, while the hair becomes, or the strands of hair become positively charged because they lost electrons. So that's one way of producing static electricity, by rubbing. Okay, so I could just add that when an object is rubbed against another, when one object is rubbed against another, electrons or particles specifically electrons, are transferred between the two objects, Now, the object with a net, or the object that, let me put it in simple terms, the object that gains the electrons becomes negatively charged, is it not? Becomes negatively charged. That's the one that gains. Gains becomes negatively charged. But the one that loses becomes positively charged. While the object that loses the electrons becomes positively charged. Becomes positively charged. All right. That's for the one that loses the electrons. So loss of electrons makes an object to become positively charged. Gain of electrons makes an object to become positively charged. So that's one way. And just like in magnetism, you know the laws of magnetism. What are the laws of magnetism?
Actually, no, I don't, sir.
you don't remember?
I don't think I remember.
Okay. It's something you know. If I mention it, you'll be surprised that it's actually something you know. Laws of magnetism: like poles repel, unlike poles attract. So the same thing applies to static electricity. Laws of electrostatic induction or static electricity. Or you can just simply say laws of statics. Number one, since we say unlike, in magnetism, like unlike poles, north and south, we do what? Attract. So in static electricity, unlike charges attract. Okay, so I can simply say unlike charges attract. Unlike charges talking about positive and negative, or negative and positive, e.g. positive and negative will attract. While like charges for like charges, we have positive and positive, and positive, or negative and negative, negative and negative, will attract, we repair. All right, I think we have built a foundation for this. We're going to build on this foundation. Okay, while like charges, we repair. In fact, when you get to higher classes in your study of sciences, you will notice that magnetic field, electric field are very related. As a matter of fact, in higher physics, we don't separate magnetic field from electric field. So we call the two electromagnetic field because they are basically together. One produces the other. A magnetic field has an electric field in it. An electric field has a magnetic field in it. You will see that as we continue. That's why you see the laws are related. There's another field force, which is gravitational field. They also behave almost the same way, except that gravitational field is only about attraction. There's no repulsion. When you have two objects, maybe you have a stone, it is attracted to the ground. Okay, let's not go there. We talk about that. So unlike charges, positive and negative will attract, while like charges, positive or negative will repel. Now another law which I think you need to know is just like a magnetism. The further you move away from the magnet, the weaker the force. So the further you move away from the charged object, the weaker the force. All right, that we can include that. The further you move away from the charged object, from a charged object, the weaker the force, the electrostatic force. In fact, at higher level, we say it obeys the law of inverse proportion, because the further you move away from it, the strength reduces by square of the distance apart. Anyway, we'll talk about that at higher level. The further you move away from a charged object, the weaker the electrostatic force. All right, let's go to another concept. Are you ready? Go to the next page. Let me introduce this. Electric field. I told you they are all related, just like we have magnetic field. What do you remember about magnetic field? This is the electric field is the region around a charged object where the electrostatic force can be felt. Just like a magnetic field is the region around a magnet where the magnetic force can be felt. You see how they are related. So this is the region around a charged object. Around a charged object where the electrostatic force can be felt. Electrostatic force can be felt. Now we represent electric field. I said the electric field is the region around the charged object where the electrostatic force can be felt. We represent electric field with electric lines. So electric lines are imaginary lines we use to represent the electric field. But you can call the electric lines of forces. So electric lines are imaginary lines. These are imaginary lines. Lines used to represent the electric field. Electric lines are imaginary lines used to represent the electric field, right? In magnetism, if you remember, magnetic lines of forces run from what pole to what pole? Oh, you do remember, from north to south. In electric lines will run from what to what? You still remember positive to negative. That's interesting. So let me add it. So electric lines run from positive from the electric lines run from the positive to the negative. Electric field patterns. Electric field patterns. Now, if you have a charged object that is spherical like this is the kind of pattern you get. Let me zoom it in so that you see it properly. Remember I told you that electric field lines run from where to where? Let me remind you. Go to the previous page. The previous page. Read what I wrote on electric lines. Can you read it out?
These are imaginary lines used to represent the electric field.
Okay, electric lines are imaginary lines used to represent the electric field. And I said electric lines run from the positive to the negative. So out of the positive towards the negative. Okay, for instance, if you have, let me represent it here before I move on to, if you have a positive plate here, that's an object that is positively charged. And then you have an object that is negatively charged here. The electric lines between the positively charged plate and the negatively charged plate will be like this. What will be the direction?
To the right.
To the right, because it comes out of the positive towards the negative. Okay, so whenever you're drawing that, we usually draw lines that are at right angles to the tangent. Look at this for a particular sphere. If I draw a tangent like this, but those things are not necessarily what you are expected to be constructing. But when you're drawing, you just ensure that it's reasonably at right angle to the tangent. Pardon?
That's 45 degrees between each one.
Did you say 45 degrees? It should be 90 degrees now.
Between each one.
How? Because this is 90 degrees. Tangent, when a tangent of a circle makes angle 90 degree with the radius. If I produce this line, make it longer, prolong it until it gets to the radius, it makes angle 90 degree with the tangent, isn't it? Okay, so we call them radial lines. It's not necessary that you have to actually do some construction, but when you are drawing, it should be reasonably at 90 degree to the tangent. Pardon?
Couldn't that mean you can draw it anywhere?
You can draw it anywhere, but like I said, there's no need for construction. In fact, if you are given this kind of question, you could just draw stuff like this. This is enough. You don't have to construct and just show that they are going out of the positive if this object is positively charged, so it will go out of it like this. Now if it is negatively charged, it will be drawn the other way, going towards it, isn't it? So let me just add that. Okay. If I have this, now this time it is negatively charged. I can also draw, I think I should draw the radial lines first before that. So I also draw radial lines coming out all around. No, remember this is negatively charged, so the radial lines, the arrows should point towards. You know, so that's basically what we do for negatively charged plates. So this is what you get. Alright, so that's the same thing if it is a point charge. If it's a point charge that is positively charged, radial lines that have arrows pointing away. Now if you have two parallel plates such that one plate is positively charged and the other plate is negatively charged, you also have lines moving from the positive side to the negative side. Now whenever the field is uniform, the spacing should be reasonably equal, because if you have a line here, you know, like lines that are closer to each other, it means the fields are more at this point.
Oh, sorry, I mean,
Yeah, the lines that are closer to each other means the fields are more, like greater field. So for a uniform field, the spacing should be reasonably equally spaced. Remember I said no need for measurement, just a reasonable drawing will be accepted. If the lines are closer, it means the field is stronger at that point. If you remember in magnetism, the closer the lines, the stronger the magnetic strength, the stronger the magnetic field at that point. But I don't want to mumble up the two. When we get to magnetism, you will see that. So also in electric field, the closer the lines, the stronger the field. So if the field is uniform, the lines should be equally spaced. You know, so this is a uniform field between a parallel plate, positively charged, and another parallel plate, negatively charged. All right. Now, the direction of the electric field. The direction of the electric field will definitely be the direction of the positive charge. Can I explain that? If you place a positive charge here, I'm going to use a blue line to place. I have an object that is a particle that is positively charged. This particle is positively charged. Which direction do you think it will go to?
Downwards.
Why will it go down?
Because the negatively charged.
Is going towards the negatively charged plate by attraction, isn't it?
Yeah.
So the direction of an electric field at any point is the direction of the force on a positive charge at that point. Sometimes you are
Okay.
exactly the direction of an electric field at any point is the direction that a positive charge at that point will move. Because a positive charge at that point will be repelled away from the positive plate and move towards the negative plate. So that's also the direction of the electric field. So an electric field is a vector quantity as it has both magnitude, which is its strength, and direction. I want to talk to you very briefly about something I am sure you know: conductors and insulators. So what are conductors and why are they conductors? Conductors and insulators, okay?
Are able to support the passage of electricity or heat.
Okay,
They are
conductors,
magnets because
yes.
they have free electrons.
Interesting, yeah. So conductors allow charges to pass through them easily, while insulators do not allow charges to pass through them. Remember, we're talking about static electricity that involves charges that are transferred and they stay where they are transferred. So, if conductors allow charges to pass through them easily, they provide a passageway for charges and they allow charges to flow. It means conductors will not be suitable for producing static electricity, because static electricity involves charges that are transferred and they stay. This is the point I'm making. You know, like when I told you about rubbing a ball pen against your hair. Electrons are transferred between the pen and the hair. You know, if electrons are transferred from the hair to the pen becomes what? That's electrostatic induction. I mean, if the electrons are transferred from the hair to the pen, what charge does the pen have? Remember, electrons are transferred from the hair to the pen, so the pen becomes negatively charged, and the pen becomes negatively charged, right? Because it gained electrons, while the hair becomes positively charged because it lost electrons. Now, the pen must continue to have those electrons, those excess electrons, to remain negatively charged. If it loses the electrons, it gets discharged, isn't it? It gets discharged immediately. The electrons flow out, as it were. So I said all of this to say this: for the pen to keep those electrons that it gained, it shouldn't be a conductor, because a conductor will allow the electrons to flow out. So yes, insulators are good for generating and keeping static electricity. Insulators, because when charges are transferred, they stay. The materials that are insulators do not allow charges to flow out of them. So I can just write a simple note. You already mentioned that conductors are materials that allow charges to pass through them easily, isn't it? So conductors are materials that allow charges to pass through them easily, and you explain that this is because they have. Are you listening? Why? Why do they allow charges to pass through them easily? Now this is because, and why do they have free electrons? This is because, okay, or can I just specify? This is because conductors have, this is a point I want you to take note of, have a weak affinity. Did you ask a question?
What's affinity?
Affinity is like an attraction. Let me put it in bracket. Attraction. Two electrons. So they can afford to donate electrons. They are actually electron donors. They have a weak affinity with electrons. Of course, that's why they have free electrons. You know, if for them to have free electrons, I mean, they really don't like electrons, as it were. So they can afford to have free, delocalized electrons floating around in between atoms. You know, that's for conductors, right? That's also why they are good at conducting heat, because those free electrons can actually carry the thermal energy faster and make the transfer of heat faster than just normal conduction from vibration of one particle to another particle. Okay, so this is because conductors have a weak affinity or attraction to electrons.
Yeah.
You know? So they have free or delocalized electrons that can easily transfer charges. That's the point. Conductors have a weak affinity or attraction to electrons, so they have free or delocalized electrons that can easily transfer charges. So when charges are transferred, you know, by the way, when I say charges are transferred, what actually moves from one particle to another particle? That's from one object to another object. Electrons. So when the electrons, for instance, if I am one object, you are another object, and we are rubbed against each other, electrons move from me to you. If you are a conductor, those electrons will still flow out through you, maybe lost. So you can't keep the electrons. Even if you became momentarily charged by getting the electrons flow out as quickly as they are transferred to you. So you can't keep them. You know, you have to keep that or those excess electrons to remain charged. I said all of that to emphasize the fact that conductors cannot be easily charged by static electricity because the charges that are transferred are easily lost because they flow out, as it were. So to produce static electricity, we use insulators. Now, insulators, you know, do not allow charges to pass through them easily. Now, I'm talking about passing through. It doesn't mean that they cannot collect. It's now passing through. For instance, one insulator rubbed against another insulator charges can be transferred, like can be passed from one object to another object. But for those charges to flow through the material, it becomes difficult. So they stay. They can't even be lost. That's for insulators. So insulators do not allow charges to pass through them easily because they have a strong affinity to electrons, strong attraction to electrons. If we were to get into chemistry, you will remember that conductors, usually metals, form positive ions. You know, when you lose electrons, you are positively charged, isn't it?
Yes.
You lose electrons, right? You are positively charged. So conductors are the ones that can easily allow those electrons to flow out and be lost. Insulators have a strong affinity to electrons. In fact, once they see an electron, they hold on to it. They don't allow it to flow through. Okay, so production and keeping of static electricity is through insulators. Because with conductors, the electrons can flow out and be lost. So insulators do not allow charges to pass through them, you know, because they have a strong affinity to electrons. So I can just add this is because they have a strong affinity to electrons. So in other words, they can hold on to the electrons that get transferred to them. If you want to keep an object charged, like I said in summary, it should be rested on an insulator. So, yes. Are you listening to me?
Yeah.
If I have a conductor, let's say a piece of iron or aluminium, and I do something on this and get charges transferred to it. I got charges transferred to it. I'm going to use this yellow line to show that charges are transferred to this piece of iron.
So the iron was negatively charged?
No, initially the iron was neutrally charged. In the natural state of atoms, they are neutrally charged. So now if I transfer charges to it, when I say transfer charges, what are the charges that are being transferred? Electrons. Electrons, which are electrons, right? Assuming it receives some electrons by rubbing or whatever. By just receiving electrons, what will be the overall charge of this ion? It's negatively charged. So to keep it negatively charged, it has to be rested on an insulator, maybe a plastic or a piece of wood, as you rightly said, So this should be an insulating stand. And even at that, it's not just enough to rest it on an insulating stand. Even the air surrounding it can be a passageway for the gained charges to leak away. Yeah, dry air is an insulator. But the air is not completely dry. Even right here we are, the air is not, it has water vapor in it. And water can conduct a little bit. So if an object is charged and it is surrounded by air, the air can allow those charges to leak away. That's why usually when you carry out this experiment, we have to round up. When you carry out this experiment, you rub this against your hair and it picks a piece of paper. Because you are holding it, after a while it doesn't pick again. When you rubbed it, it became charged. For instance, negatively charged. So you can pick up that piece of paper by attraction. But after a while, the charge leaks away either through your hand or through the surrounding air. So to keep it permanently charged after rubbing it against an object, where should I place it? On an insulator. And then it should also be surrounded by an insulating material. All right.